Good evening. This is Rabga Salim presenting our project entitled Large Acoustic Models for Visual Narration with Large Visual Embeddings. I'm representing Group 16, and to begin with, we know that sight conveys more than object detection, and it conveys context, it conveys emotion, mood, and spatial relationships. So the people who don't see, the visually impaired or the blind, they always lack the semantic layer of their surroundings. So we know that other systems have been developed, for example, the screen readers, which hand only text. And because of this, that means they cannot describe a visual scene. For example, a mere system would say a man is standing near a car instead of saying a man waits anxiously beside a taxi in a heavy rain. You see, that last statement has vision semantic meaning, and its description is expressive. So these systems should focus on why does this matter instead of just giving a little explanation. And what has been done so far, we know that assistive technologies have advanced in obstacle detection and navigation, e.g. dialogue-based systems, and also they work on cross-modal learning, for example, the SoundNet. There's also a benchmark for the VIA-LM, which show even large models struggle to ground descriptions, whereby the ChatGPT-4 responses out of the 100 responses was given, a quarter of those were grounded responses, that is 25.7%. And what's missing now? We know that existing systems, they often suffer a problem of giving a context-rich system semantic narration, whereby they only detect objects and caption them. Then also, a few efforts have been put up to make sure we have a single pipeline that has large visual embeddings and also large acoustic models. So this is a challenge, and also we lack evaluation metrics for the narration quality, which also keep undeveloped. So this work translates rich visual embeddings directly into expressive spoken narration. The problem that we're solving, it lies in giving an emotional and rational and narrative meaning, whereby the current systems give narrow and object-focused descriptions. So the gap between sighted and blind experience demands narration is expressive, semantic, and non-monotonic. They shouldn't sound robotic. And this project or this system will make sure it bridges this gap between the people who see and the people who are visually impaired by making sure they give an expressive and semantic rich narration. And like I've been saying, there is no single or an integrated pipeline that runs rich visual understanding into expressive speech, having the large visual embeddings and also the acoustic models. From the papers that we reviewed, we have the OdoSite, which is a large language model, but then its limitation lies in it focuses on dialogue-based assistance, not continuous narration. Then another one is synth audio, which converts visual scenes into non-verbal generative sounds using psychoacoustics and Foley synthesis to sonify distant scenes. Then it's limited to distant scene representation and ambience, which provides no continuous semantic narration or object-level description. Then another one is the SoundNet, which is a teacher-student model that learns acoustic embeddings from unlabeled video. Its limitation lies in whereby it operates in audio then to visual, and it stops at classification embeddings, does not generate narration, and it lacks semantic narration. Then the last one is the VIA-LM, which I've been talking about in the previous slides, that suffers a limitation of grounding. It grounds the descriptions, and this methodology was developed on a survey of 43 large language models on 200 supermarket images.
Hello everyone, my name is Nakachika Jovia, and I'm here to take you through the main objective and the specific objectives of our project. So the main objective is to develop a multimodal intelligent system that generates semantically rich and natural audio narrations for visual scenes for visually impaired. So we want to create an AI-based assistant to help these visually impaired people to understand their environment, to get to know what is happening, and then later it narrates to them in a human-like voice without the need of a translator. Then the specific objectives. The first objective is to develop a vision-based model that extracts rich visual embeddings for semantic scene understanding. So this objective helps the system to see and to pick out objects and to identify the certain figures that are in the person's surrounding. Then the second one is to design a language generation model that transforms visual embeddings into coherent contextual and story-like textual narrations. So this objective enables the system to ably translate what it has seen into narrations, into a contextual, something that has depth, something that is wholesome from what it has seen in the environment. Then the third is to implement a large acoustic model that generates natural and emotionally expressive speech from the generated text. So from the narrations, the system ought to pronounce, to verbally speak what has been identified in the scene. So that's what this objective helps the system to do. Yes, thank you very much. I'll invite the next speaker.
My name is Naomi Mnezero, and I'm going to take you through dataset description and exploratory data analysis. So we had two datasets, and the first one was Ego 4D dataset from ShareGPT video collection on Hugging Face. So this one was used for video to text component, and it was containing 500 video clips. We split them into testing, validation, and training. And also we had the second dataset, which was Alice dataset, and this one was larger and for audio to text component. It was containing 1,200 audio clips, and we also split it into testing, validation, and training. So going to exploratory data analysis, we performed EDA on our datasets to understand more the datasets, and this is a sample of some of the visualization. We have caption word count distribution on top, and this box plot shows that most words lie between 270 to 350 words, with a medium of 300 words, and this tells us that the descriptions are quite consistent in length, which is good for training. This second one on top, we looked at top 10 frequent bigrams. This bar chart highlights common phrases like video progress. This makes sense because the dataset contains mainly continuous scene descriptions and narrations. And finally, this one at the bottom is text length against audio duration, which is for the audio dataset, Alice dataset. The scatter plot shows a clear upward trend, meaning longer texts generally correspond with longer audio. This confirms that the dataset is well aligned and intentionally consistent. Thank you.
My name is Kasha Alvin Sari. I'll be taking you through the rest. So when I start with the research methodology, the video is fed into a large vision model that generates large visual embeddings that are fed into the same embedding space above the projection layer, where the language generation model generates a text narrative that is fed into the large acoustic model that generates auditory feedback to the user. Then it's just an ablation study score that shows the contribution of the large visual embeddings and how the fine-tuned Lava model outperformed its baseline model, and also just a simple generic caption model through BERT score that measures the semantic similarity between the reference text and also rather generated text and also the on-ground truth. And then this is just a narrative or narration arc score that measures how length the story-like narration generated. So with clear, you see that the Lava fine-tuned model outperformed all the other classic models. Then this is a cross entropy loss graph for the Lava Next 7 video model and also Lava 1 visual model. So this you could clearly see both of the models followed a similar pattern where by the training loss dropped gradually, and then the validation loss followed the same, and this was a null gap between the two, showing that the model was actually generalizing well on the dataset. Though the Lava 1 visual model, you could clearly see that it had some spikes in the training loss. So it was trained under 2 epochs, so I was trained out of 3 epochs. So yeah, you could clearly see that it had issues with the validation loss being nearly the same, showing that the model was actually having instances of maybe overfitting here and then it wasn't generalizing all the data set. Then next, these are just metrics used to compare the Lava Next 7B and the Lava 1 vision model. So the BERT score is about semantic similarity between the generated text and also the on-ground text. Then the log L looks at the longest common subsequence between the generated text and also the on-ground truth. Then the temporal cohort just looks at how how a model generates a narration from sentence to sentence, logically following the video. Then I already talked about the NAST, but the EEE looks at how the generated narration has emotion noted or emotional text or words in it. So you could clearly see the Lava Next 7B outperform the Lava 1 vision model in all these metrics. Then this is just the cross entropy loss of the large acoustic model known as Orpheus 3 BTTTS, and you clearly see that it had a steady decrease over the number of iteration steps, and also the validation loss also followed the same, meaning that model was actually generalizing all the data set. This is for the Owate 1B parameter TTS. But you could clearly see it also followed the same pattern. But then for the LASA 1B, you could clearly see there was a big gap between the validation loss and the training loss, meaning the model was not generalizing well on the data set. Then the generated speech samples in the test data set were transcribed using a whisper model that gave us a text. Then we referenced it to the on-ground truth and then generated the word error rate and minimum opinion score for these different models. You could clearly see that OFAS outperformed all the others with the word error rate, which is 8.3, then followed by our TTTS, which had 6.3, then the worst performed, which was the LASA. Then the minimum opinion score was the OT that came out outstanding. On the section, we chose the Lavanix video model as a visual language backbone, then Orpheus TTS as the large acoustic model. Then discussion of findings, of course, the Lavanix outperformed the Lava 1 vision, and also we just used the Orpheus simply because it offered comparable speech quality. Then it's just a sample UI of the system. So a user uploads a video, the Lavanix 7B generates the narration here in text, then it's passed into a large acoustic model that generates the audio. Then that's the conclusion. Of course, we have 522 vision language model that was the Lavanix 7B, and also Lava 1 vision model, and then 3 acoustic models, which was Orpheus, OT, and then LASA TTS. Then we successfully deployed the system having the models hosted on Hugging Face. Then Cerebium.ai offered GPU inference. Then the front end was offered, whether was hosted on Vercel. Then, of course, the results in conclusion demonstrated that technical feasibility of transforming visual understanding to expressive auditory narration for accessibility function is actually crucial. Thank you very much.